Welcome to another episode. Before we begin, I'd love to know where you're listening from and what time it is for you right now. Leave a little note in the comments. It's always amazing to see how far these stories travel and how they meet people in different moments of the day. And if you'd like to keep drifting with us into science, history, and reflection, remember to subscribe. It's the simplest way to stay connected. Tonight, we're going to follow something that seems ordinary, yet is quietly profound. Something that trails us in the sunlight, stretches long in the evening, and disappears when the night takes over. Something that shows us light not just by its presence, but by its absence. Shadows. They look simple, silhouettes carved out of brightness. But the reality is far stranger. Shadows blur and bend. They split into regions of light and darkness. And sometimes they even reveal secrets of the universe that light itself hides. From the sundials of ancient civilizations to the eclipse paths that measured the earth, to the delicate fringes that revealed the wave nature of light, shadows have always been guides into deeper mysteries. So, settle in. Let the day soften, and let's begin our quiet journey into the strange world of shadows. Shadows have been with us since the very first dawn. Long before humanity had words to describe them, long before we understood light or the sun, the earliest humans would have watched their own dark shapes stretch and shrink across the ground. Perhaps those shifting silhouettes seemed alive, as if they were spirits bound to the body, always present, yet somehow separate. Even now, thousands of years later, shadows remain both ordinary and strange. They are constant companions of light, but also reminders of mystery. We rarely stop to think about them. They fall behind us as we walk. They cling to our feet. They stretch out when the day ends. When a candle flickers, the shadows in a room dance. When the moon moves across the sun, a vast shadow brushes across the earth. Every moment of our lives is filled with shadows, and yet we pass them by as though they were nothing more than absence. But shadows are not just blank spaces. They have a structure, a texture, even a language. They are not simply where light fails to go. They are patterns shaped by geometry, physics, and perception. And in many ways, shadows reveal truths about the world that light alone does not. The philosopher Plato understood this well. Around 380 BCE, in his famous work, The Republic, Plato described what is now one of the most enduring images in philosophy, the allegory of the cave. In this story, prisoners are chained inside a dark cavern. Behind them burns a fire, and between the fire and the prisoners pass objects carried by unseen figures. The prisoners cannot turn their heads. They see only the shadows cast upon the wall in front of them. For these prisoners, the shadows are reality. They know nothing of the fire, nothing of the objects, nothing of the outside world. If one of them were released and turned to see the truth, he would at first be blinded by the light and overwhelmed by how false the shadows were. For Plato, this was a metaphor for human perception. We mistake the shadows of things, appearances, illusions, incomplete knowledge, for reality itself. True understanding requires us to turn toward the light, even if it hurts. This allegory has echoed for over 2 millennia. It's a reminder that shadows are not just physical phenomena, but symbols of perception and ignorance. Literature and art have returned to this metaphor again and again. Dante, in his Divine Comedy of the 14th century, used shadows to show the difference between the living and the dead. Shakespeare, in the 16th century, spoke of life itself as a walking shadow, a poor player that struts and frets his hour upon the stage. In Japanese aesthetics, shadows are celebrated in works like Junichiro Tanizaki's In Praise of Shadows, 1933, where dimness and obscurity are not flaws, but spaces of subtle beauty. Why do shadows carry so much weight in philosophy and art? Perhaps because they stand at the border of the seen and unseen. They are real, yet insubstantial. You can't touch a shadow, you can't put it in a jar, but you can see it, and it always points back to something else. In that sense, a shadow is both presence and absence, illusion and truth. Even language reflects this ambiguity. In English, shadow can mean a literal dark shape, but it can also mean an echo, a ghost, a diminished form, a shadow of his former self. To shadow someone is to follow them invisibly. To live in the shadow of something is to exist under its influence, often unnoticed. Carl Jung, the Swiss psychologist, took this metaphor further. He spoke of the shadow self, the parts of our psyche we repress or hide, but which nonetheless shape who we are. To confront the shadow, in Jung's view, was to face the uncomfortable truths about ourselves. From Plato to Jung, from Shakespeare to Tanizaki, shadows have been reminders that what we see is not the whole story. They hint at hidden structures, at realities we might overlook if we only stare at the light. But shadows are not only cultural or philosophical symbols. They also play a practical role in how we perceive the world. Without shadows, our sense of depth and form would be weaker. Artists have long understood this. In the Renaissance, painters like Leonardo da Vinci and Caravaggio mastered chiaroscuro, the dramatic use of light and shadow, to give figures weight and presence. A flat painting became three-dimensional when shadows were carefully placed. Light alone can dazzle, but light and shadow together create form. Even our everyday vision relies on this interplay. When you look at an object, the way shadows fall across its surface tells your brain about its shape. A ball lit from one side looks round because of its shadowed curve. A face is recognizable in part because of how light falls on its features. Shadows make the world legible. And beyond perception, shadows guide us in time and space. The earliest sundials, dating back at least to ancient Egypt around 1500 BCE, used the shadow of a stick, a gnomon, to mark the hours of the day. For millennia, humans told time by watching how shadows moved. Long before mechanical clocks, shadows measured the rhythm of life. There is also a primal, almost poetic comfort in watching shadows lengthen as the day ends. The long, stretching shadows of evening signal the coming of rest. The short, sharp shadows of noon announce the height of the sun. Even now, when few of us depend on sundials, our moods are guided by the way light and shadow change through the day. Yet despite their familiarity, shadows also unsettle us. A shadow moving when nothing is there can provoke fear. A figure half hidden in shadow is more mysterious than one shown in full light. In ghost stories, the shadow is often a sign of the uncanny, something not fully real, yet not entirely absent. The German writer Adalbert von Chamisso captured this unease in his 1814 novella Peter Schlemihl, the story of a man who sells his shadow to the devil. Deprived of it, he is shunned by society, as if his lack of shadow made him inhuman. This fear is rooted in something profound. The shadow reminds us that reality is layered, that light itself is not straightforward. We think of light as clarity, but shadows show that clarity is never complete. There are always edges, gradients, ambiguities. Science, too, has followed shadows into these ambiguities. But before we move into diffraction and penumbras, before the great experiments of the 17th and 18th centuries, it's worth pausing here, at the edge of philosophy and perception. Shadows are ordinary, yet they hold an ancient, almost mythic weight. They remind us that reality is both visible and invisible, both certain and uncertain. So the next time you see your shadow stretching across the ground, consider it more than a dark shape. Consider it a companion, a silent record of light, space, and perspective. Consider it a metaphor for the limits of what we know and the possibilities of what lies beyond. In this way, shadows are not just absences, but invitations. Invitations to look deeper, to question what we see, to remember that every brightness casts its own darkness. They shape not only how we see the world, but how we imagine it. Shadows have always been more than passing curiosities. In the ancient world, they became the first silent teachers of order in the cosmos. Imagine the desert sun high over the Nile, some 3,500 years ago. A simple stick planted in the sand throws a long, dark mark across the ground. As the hours pass, the mark shifts like the hand of a clock, sweeping steadily from west to east. At midday it shortens, hugging the stick almost completely, and then lengthens again in the opposite direction as the afternoon wears on. Long before anyone thought to craft gears and escapements, this was time itself made visible, carved by light and darkness. The earliest known sundials in Egypt, dating to around 1500 BCE, were little more than stones and sticks, yet they allowed people to break the day into smaller pieces. A fragment of limestone from the Valley of the Kings shows divisions that appear to mark hours, evidence of one of the oldest human attempts to tame the flow of sunlight into units. It was the beginning of our 24-hour cycle, dividing both day and night into 12 parts each. A rhythm of shadows shaped the rhythm of human life. But sundials did more than mark the hours. They revealed the larger pattern of the year. By observing how high the sun rose at noon on different days, ancient observers could mark the solstices and equinoxes. The changing lengths of shadows became calendars written across the earth itself. In this sense, shadows were not only clocks, but astronomers too. They allowed civilizations to predict planting seasons, religious festivals, and the return of floods. Even monuments like Stonehenge or Nabta Playa in southern Egypt seem to be aligned to the play of sunlight and shadow across the stones, suggesting a sacred dimension to this knowledge. Centuries later, when philosophy began to blossom in Greece, shadows continued to inspire thought. Aristotle, writing in the 4th century BCE, gave shadows a more formal dignity. He was fascinated by their geometry. He noticed that during a lunar eclipse, when the Earth slipped between the Sun and the Moon, the shadow of the Earth always appeared circular. No matter where the eclipse took place, the curve of that shadow was smooth and round. To him, this was clear evidence that the Earth itself must be a sphere, for only a sphere always casts a round shadow. It was a simple observation, but profound. The form of our planet, written in darkness upon the face of the moon. Aristotle was also intrigued by the behavior of shadows in daily life. He asked why they seemed sharper in some circumstances and blurred in others, why they grew longer or shorter with distance. Though he lacked the language of modern optics, his careful attention showed that shadows were not empty, but phenomena to be studied, patterns with rules waiting to be discovered. In the bustling city of Alexandria, some centuries later, Claudius Ptolemy carried this tradition further. His great compendium, the Almagest, drew upon generations of observations, and shadows were central to its geometry of the heavens. With a vertical rod and a steady eye, one could track the maximum height of the sun, and from this, calculate latitude. A traveler moving north or south could learn his position on the earth simply by comparing the length of shadows at noon. Such methods were not abstractions, but practical tools, especially for sailors navigating the Mediterranean. Shadows turned into instruments of geography. The legacy of these ideas spread far beyond Greece. In the Islamic Golden Age, between the 9th and 13th centuries, scholars refined shadow science with a precision that astonishes even today. Ibn al-Haytham, known in the West as Al-Hazan, wrote his Book of Optics around 1021 CE, carefully describing how light travels and how shadows form. He experimented with pinholes, demonstrating how rays project inverted images, anticipating the camera obscura. Shadows became the foundation of an entire science of vision. Others, like al-Battani and al-Biruni, used gnomons and elaborate shadow instruments to refine calendars and prayer times. At the Maraga Observatory in Persia, enormous structures were erected to measure the length of shadows at noon with meticulous accuracy. For them, shadows were precise data, no less reliable than the stars themselves. Yet perhaps the most elegant triumph of shadow-based reasoning came earlier, from Eratosthenes of Cyrene, working in Alexandria around 240 BCE. He had heard reports from Siena, a city far to the south, that at noon on the summer solstice, the sun stood directly overhead. Wells were lit all the way to their bottoms, and vertical sticks cast no shadows at all. On the very same day, at the same time, Eratosthenes looked at a stick in Alexandria and found that it did cast a shadow, tilted at an angle of about 7 degrees. That simple difference carried enormous meaning. If the earth were flat, the sun's rays would fall at the same angle everywhere. The fact that shadows diverged suggested the earth was curved. Eratosthenes knew the approximate distance between Siena and Alexandria, about 800 kilometers, measured by caravan journeys along the Nile. If 7 degrees of curvature corresponded to that distance, then 360 degrees would correspond to the full circumference of the planet. With a straightforward proportion, he calculated the Earth's circumference as roughly 40,000 kilometers. The actual value at the equator is about 40,075 kilometers. With little more than a stick, a shadow, and a sharp mind, Eratosthenes had measured the size of the world to an error of less than 1%. Few experiments in history are at once so simple and so majestic. From darkness on the ground, he had grasped the dimensions of the earth itself. It is worth pausing to appreciate the beauty of this. Shadows, which seem like mere absences, proved to be rich with information. They told us not only what time it was, but where we were, how the earth curved beneath us, even the total span of the globe. The absence of light became a path to understanding the structure of reality. For ancient peoples, shadows were therefore never meaningless. They were companions in daily life, guides in travel, and signs in the sky. They carried practical weight, but they also carried symbolic weight. To follow the path of a shadow was to align oneself with cosmic order. To measure its angle was to measure one's place in the universe. As the centuries unfolded, shadows would continue to guide science. They would reveal subtler mysteries, why the edges blur, why they bend, why darkness sometimes glows. But even before those discoveries, shadows had already transformed our understanding. They gave us clocks, calendars, and the circumference of the earth. They showed us that knowledge could come not only from what shines, but from what stands in the way of shining. When we look back, we see that shadows were among our first scientific teachers. A stick in the sand became a clock. A dark curve across the moon proved the earth was round. A narrow angle in Alexandria gave us the size of the world. From the simplest of observations, extraordinary truths emerged. Light may dazzle, but it is in the quiet trace of shadows that some of humanity's earliest insights were born. When we think of a shadow, we often imagine a crisp silhouette, the kind that a midday sun throws onto a stone pavement. A child stretches out an arm, and the outline is sharp and faithful, every finger traced in darkness. But not all shadows are so precise. Hold your hand near a candle, and the edges blur. The darkness fades into light, soft and uncertain. What seems like a simple absence is in fact a spectrum, a gradient born from the geometry of light itself. The difference lies in the source. The sun, though unimaginably large, is so distant that its rays reach us nearly parallel. A candle flame, by contrast, is close and broad, radiating light in many directions. When an object blocks only part of this light, the result is not a single clear shadow, but a combination of regions. The darkest part, where all rays are blocked, is called the umbra. The lighter fringe, where only some rays are blocked while others slip past, is the penumbra. And under certain conditions, a third region emerges, the antumbra. where the object appears smaller than the light source, leaving a ring of brightness around its shadow. These terms sound technical, but they describe phenomena we all see. Place a ball between a lamp and a wall, and you will notice the soft halo around the central darkness. Step outside during a partial solar eclipse, and the ground is covered in crescents, overlapping penumbras from the small gaps between leaves. Stand within the full shadow of the moon during a total eclipse, and you are inside the umbra, gazing up at a sky gone black in the middle of the day. Watch from farther away, and the moon seems to shrink within the sun's glare, casting an antumbra that produces the haunting sight of an annular eclipse, a fiery ring suspended in the heavens. The naming of these regions came slowly. The Latin roots are simple enough. Umbra for shadow, penumbra for almost shadow, antumbra for opposite shadow. But the concepts were clarified gradually as astronomers and natural philosophers tried to reconcile what they saw with what they expected. Aristotle had noted the blurring of shadows, but without the tools to describe light as rays, his explanations were necessarily incomplete. For centuries, the geometry of shadows puzzled observers, especially during eclipses. The Renaissance brought a fresh precision. Galileo Galilei, peering through his telescope in the early 17th century, noticed that the moon itself seemed shaded, its craters producing tiny gradations of darkness. The terminator line, the boundary between lunar day and night, was never razor-sharp, but softly shaded, a planetary penumbra written in grey dust. He realized that shadows reveal not only the geometry of light, but the texture of the surface that receives it. The jagged mountains of the moon stretched their shadows across plains, and from their lengths he could estimate their height. Darkness became a ruler. Johannes Kepler, Galileo's contemporary, pursued shadows with equal intensity. He coined the very word photometer and studied how light spreads and diminishes. In his work, Astronomiae Pars Optica, 1604, he described how eclipses unfold, distinguishing between the regions of umbra and penumbra. For Kepler, the soft edges of shadows were not imperfections, but evidence of the finite size of celestial bodies. A small sun would cast sharp shadows. A vast one, even at a distance, gave rise to fringes. He used this reasoning to describe planetary transits and eclipses, offering one of the first rigorous geometrical accounts of how light and shadow interact in space. If Galileo used shadows to measure mountains on the moon, Kepler used them to measure the heavens themselves. The penumbra, once a vague blur, became a calculable quantity, a region that could predict the duration of an eclipse or the visibility of a transit. Shadows were no longer incidental, they were instruments of astronomy. But even in the domestic world, people had long been aware of how different light sources changed the character of shadows. Candlelight filled rooms with soft, trembling edges. A fire cast sprawling, uncertain forms on cave walls or plaster ceilings. Sunlight, in contrast, gave crisp silhouettes that artists could trace. During the Renaissance, this contrast was exploited in art as much as in science. Painters like Caravaggio plunged figures into chiaroscuro, manipulating sharp umbras against diffuse penumbras to heighten drama. The physics of shadows became tools of expression. Eclipses provided the most spectacular demonstrations. The umbra of the moon racing across the Earth during a total solar eclipse is a shadow on a planetary scale, narrowing to a path only a few hundred kilometers wide. To stand within it is to be enveloped in cosmic geometry. The penumbra, by contrast, is far larger, sweeping across continents, offering only a partial dimming of the sun. Travelers would plan journeys across countries to place themselves precisely in the umbra, just as Eratosthenes once measured angles in Alexandria. The difference between totality and partiality lay in the subtle edge of a shadow. There is a quiet poetry in the way these regions illustrate the finiteness of light. If the sun were truly an infinitely distant point, there would be no penumbra, no softness, only clean silhouettes. The blur at the edge of every shadow is a reminder that even the sun has breadth, that it is not just an abstract source, but a blazing sphere suspended in space. When you see your own shadow fraying at the edges on a sunny afternoon, you are glimpsing in miniature the geometry of the solar system. In the 16th and 17th centuries, as Europe's scientific revolution unfolded, shadows began to move from mere curiosities to rigorous subjects of study. The Jesuit mathematician Christoph Scheiner, for instance, examined the sun's own shadows by observing sunspots through a telescope, realizing that their penumbral fringes revealed the sun's spherical form. Shadow science became solar science. It is striking to think how much could be learned simply from paying attention to the soft or sharp edge of darkness. To us, shadows may seem passive, yet to Galileo, Kepler, and their contemporaries, they were active messengers, whispering of distances, sizes, and textures. The shadow of a mountain measured its height. The penumbra of the moon revealed the scale of the sun. A candle's halo explained why our own hands looked different in firelight than in daylight. Even today, children notice these things instinctively. Place a hand over a lamp, and they marvel at the blurred outline, the strange glow that sneaks around the edges. Place the same hand under the noonday sun, and suddenly the fingers are etched sharply, almost theatrically, on the ground. Without knowing it, they are rediscovering the concepts of umbra and penumbra. It is a lesson taught by light, geometry, and the simplest of observations. The antumbra, rarer and stranger, holds its own allure. It is the region where an object, though aligned with the light source, appears smaller than it, producing not darkness, but a luminous ring. This is the realm of annular eclipses, when the moon is too far from Earth to cover the sun completely. Instead of day turning to night, the sky becomes a ring of fire. The shadow is incomplete, the darkness punctured by light. Standing in an antumbra is to witness the cosmic dance between scale and distance. It is a reminder that shadows are not fixed things, but dynamic relationships between objects and light. What threads all these examples together is the realization that shadows are not uniform, not monolithic. They contain regions, gradients, subtleties. Their softness or sharpness depends not on the object alone, but on the breadth of the light and the distance between them. This was the shift that Renaissance science crystallized, to see shadows not as simple silhouettes, but as measurable, layered phenomena. And there is a kind of philosophical echo in that realization. We often think of truth and falsehood as sharply divided, like a clean shadow against the wall. But reality is more often a penumbra, a blending of clarity and uncertainty, where edges blur and boundaries soften. The same lesson that Galileo learned from lunar craters and Kepler from eclipses can be carried into human thought. The borders of things are rarely absolute. Shadows remind us that even darkness has shades. By the early modern era, shadows had become laboratories of their own. Artists honed them, scientists measured them, astronomers predicted them. They became bridges between everyday perception and cosmic geometry. The blur of a candle flame and the ring of fire in the sky were no longer disconnected curiosities, but expressions of the same underlying principles. Light spreads, objects block, shadows form, but always with gradations that reveal the finiteness of sources, the distances of bodies, and the subtlety of perception. To see an umbra, a penumbra, or an antumbra is to see the geometry of the universe in action. It is to recognize that the softness at the edge of your hand's shadow and the blazing circle of an annular eclipse are siblings, bound by the same play of light. Renaissance thinkers, standing with their telescopes and compasses, recognized this kinship and began to describe it with words and diagrams. But the shadows themselves have been teaching it for as long as there has been light and eyes to notice. Shadows are supposed to obey geometry. A solid object blocks light, leaving a region of darkness. The edges may blur depending on the size of the source, but the principle seems straightforward. Light travels in straight lines, and whatever lies in its path is marked by shadow. Yet by the 17th century, curious observers began to notice something unsettling. Sometimes shadows did not behave like strict silhouettes. Their edges frayed, rippled, or seemed to soften in ways that geometry alone could not explain. In these disturbances lay the beginnings of a revolution in our understanding of light. One of the first to look closely was Francesco Maria Grimaldi, a Jesuit priest and physicist working in Bologna in the 1660s. With patience and precision, he directed beams of sunlight through small apertures and studied the shadows of thin wires and knife edges. What he saw was strange. The darkness did not fall sharply, as one might expect, but spread into delicate fringes. At the boundaries of the shadow, narrow bands of light and dark appeared, like ripples overlapping on the surface of water. It was as if the shadow had a texture, a hidden order shimmering at its edge. Grimaldi recognized that something deeper was at play. Light, he realized, was not simply blocked like arrows hitting a shield. Instead, it seemed to bend slightly as it passed the edges of objects, spilling into regions that geometry declared should have been dark. He coined a new term for this behavior, diffraction, from the Latin diffringere, meaning to break apart. Light, in his experiments, was breaking the simple rules of straight lines, curving subtly as though it had a wave-like character. This was a bold idea, but it was also unsettling. The prevailing view at the time, especially following René Descartes and later Isaac Newton, was that light was composed of tiny particles, corpuscles, that traveled in straight lines. If light were made of such particles, how could it bend around corners? Grimaldi's careful descriptions could not be dismissed, but they left a troubling gap. If light diffracted, then perhaps it was not merely a stream of particles, but something more fluid, more wave-like. The question lingered unresolved for over a century, until an English physician-turned-physicist named Thomas Young carried the inquiry forward in 1801. Young, fascinated by language as much as physics, once helped decipher the Rosetta Stone. But his experiments with light would prove equally groundbreaking. He set up an arrangement so simple that it now appears in nearly every physics textbook. A beam of sunlight allowed to pass through two narrow slits, side by side, and then fall onto a screen. If light were composed purely of particles, one would expect to see two bright bands matching the slits. But what Young observed was far stranger, a pattern of alternating bright and dark fringes spreading across the screen. The two beams of light did not simply pass independently through the slits. They overlapped, interfering with one another like ripples on a pond. Where the peaks of these ripples met, light intensified. Where peaks met troughs, they cancelled, leaving darkness. The result was an interference pattern, unmistakably the behavior of waves. Shadows played a central role in this discovery. The darkness between the bright fringes was not caused by any object blocking the light. It was caused by light cancelling itself, a concept unthinkable if light were only particles. Young's double-slit experiment, as it came to be known, was one of the most beautiful proofs in the history of science, simple in apparatus, profound in implication. Light had a dual nature, behaving like waves on the edge of shadows. Young's results were not immediately accepted. Newton's authority still loomed large, and the particle theory of light seemed more intuitive. But in the early 19th century, another figure would provide overwhelming confirmation: Augustin Jean Fresnel, a French engineer and physicist. Fresnel was a man of delicate health but powerful imagination. Working in the 1810s, on the same problem of diffraction that had intrigued Grimaldi and Young. Fresnel developed a full mathematical theory of wave optics, building on the principle that light traveled as a wavefront, spreading outward, much like ripples in water. He calculated how waves would overlap at the edges of obstacles, predicting not only the general fringes of diffraction, but the fine details of the patterns. When he presented his work to the French Academy of Sciences, the great physicist Siméon Denis Poisson, a staunch supporter of Newton's particle theory, tried to use Fresnel's mathematics against him. Poisson pointed out a strange consequence of Fresnel's wave model. If it were correct, then a perfectly round object placed in a beam of light should produce a surprising effect. At the very center of its shadow, there should appear a bright spot, a small island of light where geometry would demand total darkness. This seemed absurd, a reductio ad absurdum meant to discredit Fresnel. But the Academy's judges, intrigued, decided to test it. Dominique Arago, another physicist, carried out the experiment by placing a small circular disk in a parallel beam of sunlight. To everyone's astonishment, at the very heart of the shadow appeared a bright dot, just as Fresnel's theory predicted. The so-called Poisson's spot, or Fresnel spot, became one of the most striking demonstrations of wave optics. A point of light glowing within darkness was enough to convince many skeptics. Shadows themselves had betrayed the wave nature of light. It is difficult to imagine how unsettling this must have been. For centuries, shadows had seemed like passive absences, simple silhouettes. Now they revealed patterns, fringes, and even bright centers. They were not inert, but dynamic, shaped by the superposition of waves. Darkness had structure. What is remarkable is how these discoveries drew from such ordinary observations. Grimaldi watching a faint shimmer at the edge of a wire, Young letting sunlight pass through two slits, Fresnel predicting a speck of light in the middle of a shadow. None of these required elaborate instruments. They required attention, patience, and the courage to believe what the eye saw, even when it contradicted the reigning theories. The implications of diffraction spread far beyond shadows. Once light was accepted as a wave, physicists began to understand phenomena like polarization, interference colors, and eventually the electromagnetic theory of James Clerk Maxwell in the mid-19th century. Shadows had led, step by step, to the recognition that light was part of a larger, wave-filled universe. And yet the story did not end there. In the 20th century, quantum mechanics reintroduced particles, this time as photons, bringing back the corpuscular picture. But even then, the double-slit experiment remained central. When photons are sent one at a time through the slits, the interference pattern still emerges over time. Light behaves as both particle and wave, and shadows still record this duality. The bending and fringes at the edges remain among the most beautiful illustrations of the quantum world. There is something poetic in the way a shadow, something so common and overlooked, became the stage for such profound revelations. What seemed like a blur at the edge of darkness turned out to be the signature of waves. What looked like a contradiction at the center of a shadow proved a new theory right. The dark was never empty. It was full of structure waiting to be seen. And in a way, this echoes the philosophical traditions that had long used shadows as metaphors. Plato saw them as illusions masking deeper truths. Jung saw them as the hidden parts of the self. The physicists of the 17th through 19th centuries discovered that even literal shadows conceal hidden patterns. In their frayed edges and paradoxical bright spots, shadows whispered that the universe was not built on straight lines and particles alone, but on waves, interference, and subtleties beyond the obvious. The next time you notice a shadow blurring at its boundary, you are seeing the same phenomenon that confounded Newtonians and inspired Fresnel. The faint halo around a leaf or a railing in sunlight is diffraction in action. The darkness is never perfectly dark. It is woven with the geometry of waves. To look closely at a shadow is to see the fingerprint of light's dual nature, written in softness and shimmer at the edge of absence. In the centuries after Fresnel's bright spot startled the French Academy, shadows continued to serve as quiet messengers of light's mysteries. What began with simple observations of blurred edges grew into a modern physics that would upend our deepest assumptions. Shadows, those familiar companions of our daily lives, became stages on which quantum uncertainty, atomic structure, and the vast scale of black holes revealed themselves. The first great shift of the 20th century was the recognition that light is not only a wave. The triumph of wave theory in the 1800s seemed secure. Interference, diffraction, polarization, and the success of Maxwell's electromagnetic theory all pointed to a universe where light was a continuous oscillation in space. But shadows once again disrupted certainty. In 1905, Albert Einstein explained the photoelectric effect, the strange observation that shining light on a metal could eject electrons. The energy of the ejected electrons depended not on the intensity of the light, as wave theory predicted, but on its frequency. A dim violet beam could eject electrons, while a bright red beam could not. Einstein suggested that light was quantized. It arrived in discrete packets, later called photons. This reintroduced the particle view of light, but without discarding its wave behavior. Suddenly, a shadow was not merely the interference of waves, but also the trace of countless photons, each choosing a path or being absorbed. The double-slit experiment, already elegant in Young's time, took on a new, almost unsettling meaning. When photons are sent one by one through the slits, the interference pattern still builds up over time. Each photon behaves like a wave, interfering with itself, and yet when detected, it lands as a particle. The shadow fringes on the screen are both wave and particle at once, a paradox made visible. This wave-particle duality remains one of the most haunting features of modern physics. Shadows are no longer passive silhouettes. They are records of light's inner contradiction. Each band of brightness and darkness in a double-slit interference pattern is a kind of cosmic handwriting, telling us that reality is not either-or, but both and. We live in a world where shadows are written by particles behaving like waves, and waves collapsing into particles. The lesson of diffraction did not remain confined to visible light. In the early 20th century, physicists extended these ideas to particles themselves. In 1927, Clinton Davison and Lester Germer at Bell Labs observed that electrons, when fired at a nickel crystal, produced a diffraction pattern, bright and dark regions arranged like waves interfering. It was as though matter itself could cast interference shadows. This experiment confirmed Louis de Broglie's radical hypothesis. Particles have wavelengths. The electron, so fundamental to the structure of matter, was also a wave. The discovery earned Davison the Nobel Prize and established wave-particle duality not just for photons but for matter itself. Shadows now revealed what could not be seen by any lens. X-ray diffraction, pioneered by Max von Laue in 1912 and perfected by William and Lawrence Bragg, became a powerful method for uncovering the structure of crystals. By directing X-rays, waves far shorter than visible light, at a crystal lattice, scientists observed patterns of bright and dark spots. These diffraction shadows acted as fingerprints of atomic arrangement. From them, the hidden geometry of matter was reconstructed. This technique transformed science. In 1953, James Watson and Francis Crick relied on Rosalind Franklin's famous X-ray diffraction images to decipher the double helix structure of DNA. The photograph, sometimes called Photo 51, is itself an image of shadows, X-rays diffracted by the repeating spiral of nucleotides. Without those dark and light streaks, the secret of life's blueprint might have remained hidden for decades longer. Shadows here were not just absences, but revelations, showing how atoms assemble into the spirals of life. The same principle expanded into electron diffraction and later electron microscopy. By using electrons instead of light, with their even shorter wavelengths, scientists could resolve structures at the scale of individual atoms. The shadows cast by electrons passing through thin films revealed arrangements invisible to any optical microscope. Our modern images of viruses, proteins, and nanomaterials owe their existence to shadows on the quantum scale. But shadows also speak on the largest scales. For millennia, eclipses had been the most dramatic reminders of cosmic shadow play. The moon slipping into Earth's umbra during a lunar eclipse, or Earth plunging into the moon's penumbra during a solar one. These events were not only spectacles, but opportunities for science. In 1919, Arthur Eddington led expeditions to observe a solar eclipse, using the temporary darkness to photograph stars near the sun's edge. The results confirmed Einstein's general relativity, light from distant stars bent around the sun, curving space itself. The shadow of the moon had provided the stage for one of the most profound demonstrations of gravity's nature. In 2019, a new eclipse-like shadow captured the world's imagination. The Event Horizon Telescope, a network of radio observatories spread across Earth, produced the first image of a black hole's shadow. Located in the galaxy M87, 55 million light-years away, this supermassive black hole revealed itself not directly, but through the darkness it cast on glowing plasma. The shadow was a circle of absence, edged by a ring of light bent by gravity to extremes. Here, on scales beyond imagination, a shadow confirmed the predictions of relativity once again. It was the echo of a place from which no light could escape, a literal embodiment of cosmic darkness. Shadows in modern physics, then, are not trivial byproducts. They are the essential marks of wave interference, the fingerprints of atomic lattices, the outlines of the most massive objects in the universe. From the nanoscale to the cosmic, absence is information. Quantum mechanics takes the metaphor further still. In this realm, shadows are not only visible phenomena, but also conceptual boundaries. Werner Heisenberg's uncertainty principle tells us that certain pairs of properties, like position and momentum, cannot both be known precisely. To measure one sharply is to blur the other, as though reality itself carries penumbras of indeterminacy. Every attempt to illuminate a quantum system casts a shadow of ignorance in another direction. The more tightly you pin down an electron's place, the more its momentum spreads into uncertainty. In quantum experiments, even shadows of possibility play a role. In the phenomenon of quantum erasure, photons that would normally produce an interference shadow pattern lose that pattern if information about their paths becomes knowable, even if no one actually observes it. The mere potential for knowledge alters the outcome. In these experiments, the shadow is not on a screen, but in the probabilities themselves, a reminder that quantum reality resists being seen in full light. This intertwining of shadows and uncertainty forces us to confront the limits of what we can know. Just as a penumbra softens the edge between light and dark, quantum shadows soften the edge between determinacy and indeterminacy. Physics, at its most fundamental level, is no longer about uncovering absolute silhouettes, but about understanding the gradients of possibility. What began with a Jesuit priest noticing fringes in Bologna has grown into a universe where shadows map everything from DNA spirals to black holes. Grimaldi's diffraction fringes became Young's interference shadows, Fresnel's bright spot, Einstein's photons, Franklin's X-ray images, and the Event Horizon Telescope's black void. Each step reminds us that shadows are never simple. They are structured, layered, sometimes paradoxical. They reveal both the wave and particle faces of reality, both the intimacy of atoms and the vastness of galaxies. And perhaps it is fitting that shadows, often seen as mere absences, should carry so much information. They remind us that the universe does not only speak in brightness, sometimes it whispers in darkness. The fringes, the voids, the blurred edges. These are as eloquent as any beam of light. To study shadows is to listen to the universe's negative space, to read the shapes cast by what stands in the way of shining. In our everyday lives, it is easy to forget this. We step over our own shadows without thought, dismissing them as silhouettes with no substance. Yet every dark outline on the pavement contains echoes of wave interference, the history of quantum physics, the proof of relativity. In every penumbra is a reminder that even the sun is not infinite. In every diffraction halo, a reminder that light bends like ripples. To stand in a shadow is to stand at the intersection of simplicity and mystery, where the absence of light reveals the deepest truths of the universe. Beyond laboratories and telescopes, shadows have long occupied another realm, the imagination. While scientists measured their angles and fringes, artists and storytellers found in shadows a language of depth, mood, and mystery. If in physics shadows revealed the structure of light, in culture they revealed the structure of the human mind. In the Renaissance, painters discovered that shadows could bring flat surfaces to life. Before this, many medieval artworks depicted figures with little sense of volume, as if humans were patterns on a tapestry. But in the 15th and 16th centuries, artists like Leonardo da Vinci and Caravaggio embraced a technique known as chiaroscuro, literally light-dark. With it, they used shadows not just as background but as sculpting tools, shaping faces and bodies with gradations of darkness. The effect was dramatic. A figure seemed to emerge from the canvas, as if carved from space itself. Caravaggio, in particular, was notorious for plunging scenes into inky shadows, then piercing them with sharp beams of light, creating tension between seen and unseen. His paintings became visual dramas of shadow and illumination. Leonardo was more restrained, but equally fascinated. In his notebooks, he carefully described how light falls on curved surfaces, how shadows soften at edges, how reflected light fills even the darkest regions with faint glows. To him, understanding shadows was essential for understanding reality. A painter who ignored them would never capture truth. Through art, shadows became more than absences. They became positive presences, as necessary as light for rendering the world. Elsewhere, entire traditions arose around shadows as performance. In Japan, shadows were celebrated in aesthetics that valued subtlety and impermanence. Junichiro Tanizaki, in his 1933 essay, In Praise of Shadows, described the beauty of dim spaces, the quiet atmosphere created by lantern glow and deep corners. For Tanizaki, brightness was not always preferable. Shadows gave objects dignity, mystery, and depth. A lacquered bowl gleamed differently in a dark alcove than under harsh electric light. In shadows, beauty breathed. Far to the south, in Indonesia, shadow became literal theatre. The wayang kulit, or shadow puppet play, has been performed for centuries, using flat leather puppets held against a screen lit from behind. Audiences sit on the other side, watching stories unfold in silhouettes. These performances retell epics like the Ramayana and Mahabharata, but their power lies in the interplay of light and shadow. A flickering lamp transforms cut-out shapes into living figures, battles, and gods. The shadows are ephemeral, vanishing when the flame is extinguished, yet in their moment they are full of meaning. It is no coincidence that in many cultures, shadow plays became metaphors for the human condition, a reminder that life itself is fleeting performance cast upon the screen of time. But shadows do not live only on canvases and stages. They live inside us. In the early 20th century, the Swiss psychologist Carl Jung introduced the idea of the shadow self. For Jung, Each of us carries within a collection of traits, desires, and fears that we repress or deny, aspects of ourselves we would rather not acknowledge. This hidden counterpart, the shadow, lurks in the unconscious, shaping our behavior in subtle ways. To encounter the shadow is often uncomfortable. It is to face impulses we would rather not admit. Yet Jung believed that integration of the shadow was essential for wholeness. Ignoring it only gave it more power. Acknowledging it brought balance. The metaphor is striking. Just as physical shadows reveal that light always has a counterpart, Jung's psychology suggested that personality always has a darker twin. We live not only in illumination, but also in obscurity, and to pretend otherwise is to live half a life. In therapy and in art, the exploration of the shadow self became a way of confronting what is hidden and finding growth in it. Beyond psychology, shadows have carried cultural meanings that range from fear to reverence. In folklore, shadows often appear as doubles of the soul. To lose one's shadow, as in Adalbert von Chamisso's tale Peter Schlemiel, is to lose humanity itself. In some traditions, stepping on another's shadow was once thought to bring harm, as if the shadow were a vital extension of life. In other myths, shadows were seen as omens, harbingers of misfortune. They were reminders of mortality, that just as light fades into darkness, so life fades into death. Yet shadows are not always sinister. In many spiritual traditions, they represent protection, a cool refuge from blazing sun. Ancient desert cultures valued shade as sacred. Even in language, we speak of resting in the shadow of someone or something, implying shelter as much as subordination. Shadows, like night, are ambivalent. They can be threatening or comforting, frightening or safe. Poets have long been drawn to this ambiguity. Shakespeare called life itself a walking shadow, a poor player that struts and frets his hour upon the stage. Here the shadow symbolizes transience, the fleeting nature of existence. Others saw in shadows the very interplay of human experience. Emily Dickinson, writing in the 19th century, observed, "We never know how high we are till we are called to rise, and then, if we are true to plan, our statures touch the skies." In her verses, shadows are often metaphors for the unspoken, the invisible counterpart of light. The philosopher Gaston Bachelard, in the 20th century, wrote of shadows as part of the poetics of space. Corners of rooms, filled with dimness, invited reverie. Darkness was not emptiness, but intimacy. In the half-lit, imagination stirs. And in ordinary life, we all feel this instinctively. A walk at dusk is different from a walk at noon. The same street, in shadow, acquires mystery. A child making shadow puppets on a bedroom wall experiences the first thrill of creation. Figures brought to life from nothing more than hands and light. Lovers walking side by side sometimes glance down at their elongated forms on the pavement, as if their shadows walk hand in hand too. Shadows are reminders that we are never fully alone, that even light leaves its companion. Perhaps what unites all these cultural, artistic, and psychological threads is the idea that shadows remind us of duality. We live always between light and dark, between what is seen and what is hidden, between clarity and mystery. To deny shadows is to deny half of experience. To embrace them is to live more fully, acknowledging that every brightness casts its outline. The modern world, saturated with artificial light, sometimes tempts us to erase shadows. Neon, screens, and spotlights flatten the subtle gradients that earlier generations lived within. But shadows remain, stubbornly, in corners and evenings, in eclipses and dim rooms. They wait for us to notice them again, to remember that beauty is often found not in absolute clarity, but in contrast, in the soft penumbra where imagination takes root. And so, shadows beyond science return us to the same lesson as shadows within science. They are never empty. They are full of presence, meaning, and possibility. Whether in the chiaroscuro of a Caravaggio canvas, the silhouettes of a wayang performance, the depths of Jungian psychology, or the whispered metaphors of poetry, shadows tell us that the world is not made of pure light. It is made of the dance between light and darkness, and we exist always in that in-between. To pay attention to shadows is to pay attention to life itself, to its mysteries, its fears, its comforts, and its beauty. They are companions of the visible and invisible, the real and the imagined, the scientific and the poetic. They remind us that every illumination comes with a counterpart, and that in those outlines and obscurities we may find truths as profound as those revealed in brightness. Shadows remind us that the world is never only what it seems. They are bridges between the visible and the invisible, stretched across our days like quiet companions. At first, they appear simple, nothing more than the absence of light. But when we linger with them, when we allow ourselves to notice, we discover that they hold entire worlds. They reveal the physics of light, bending at edges and weaving patterns of interference. They reveal the shape of our planet, the scale of the cosmos, and even the structure of life itself. They have guided astronomers, inspired artists, and whispered to philosophers. And beyond science, they carry metaphor, showing us that what is hidden can be as meaningful as what is revealed, that absence is never empty, but full of suggestion. Perhaps that is why shadows have unsettled and comforted us in equal measure. They remind us that clarity is not the whole story, that truth often lives in gradients and penumbras. They speak to the duality of human experience, the known and the unknown, the conscious and the unconscious, the bright and the dark. And in their subtle presence, they suggest a deeper truth, that to see fully, we must accept both. As this journey comes to a close, I invite you to notice the next shadow you encounter. It might be the delicate outline of your hand against a wall, or the long stretch of a tree across a sidewalk, or the dimming of a room as evening sets in. Take a moment to see it not just as darkness, but as a companion of light, a reminder that even in the most ordinary places, mysteries are waiting. And if you've enjoyed wandering through these reflections, I'd love to hear where you are listening from and what time it is for you right now. Share a little note in the comments, and if you'd like to return for more journeys like this, consider subscribing. It's a way to keep this quiet space alive, a place where we can meet again between science and story, light and shadow. For now, rest easy, let the last of the day soften, and let your own shadow keep you company until the light returns.